Okay, when we left off in our previous section, we've been talking about how we organize matter, and we went down the left side of this tree where we talked about pure substances and a little bit about how we would identify that something was a pure substance. Remember, if we decide that the matter we're looking at is a pure substance, it means that if I'm going to separate molecules from each other or elements from each other, I have to do it chemically. What we're going to talk about in this section is the other half of our tree. If matter isn't qualified as a pure substance, then it's qualified as a mixture. And that means that we can actually physically separate the parts of the mixture. I'm going to give you a really easy one to sort of help make this make sense. One type of mixture would be a pepperoni pizza. We can see the pepperoni distinctly from the cheese and from the crust and from the sauce. And if we wanted to, we could physically pick all the pepperonis off the pizza. Now, that's a very exaggerated, albeit true example, but keep that kind of in mind as we go through this. There are two types of mixtures, okay? And those are called homogeneous mixtures or heterogeneous mixtures, right? And if you've had biology, then you will probably remember terms like homozygous or heterozygous. The prefix for homo means same. The prefix hetero means different. And those are handy definitions to remember as we talk about what these mixtures look like. It doesn't matter if my mixture is homogeneous or heterogeneous, I can still physically separate the components of these mixtures. So let's deal with our homogeneous mixtures here. Another term for homogeneous mixtures is solution, okay? And I'm going to give you an example. If I take rubbing alcohol and I pour it in water, what I have is a mixture. The rubbing alcohol does not chemically combine or attach itself to water molecules. It disperses itself evenly, and even though I cannot see the rubbing alcohol separate from the water, I could take advantage of the boiling points of these two liquids, and I could separate the water from the rubbing alcohol if I chose. Solutions, also known as homogeneous mixtures because they look the same all the way through, are often also referred to as clear liquids. Now, that doesn't mean they're without color. It means that light will pass through this liquid and not be reflected. The other type of mixture, the other big category is heterogeneous mixture. And you can see the two boxes there, so you can tell that we're going to have two types of heterogeneous mixtures. The two types of heterogeneous mixtures are colloids and suspensions. Now, what makes homogeneous mixtures different from heterogeneous? Well, all homogeneous mixtures, also known as solutions, look uniform to the naked eye. You will not see the different components. In heterogeneous mixtures, you will be able to see the different components. Even if you have to maybe use a magnifying glass or a microscope, you would be able to see the distinct pieces or parts of these mixtures. So then there has to be a difference between colloids and suspensions. Well, it turns out that the difference between all of these three, solution, colloid, and suspension, the difference is in the size of particles that are in the mixture. In solutions, the particles that are dispersed in the medium are so small that you don't really necessarily see them easily, but they stay uniformly mixed. In colloids and suspensions, the particle sizes are bigger. So we're going from solution particles are smaller than colloids, and colloid particles are smaller than suspensions. In colloids, the particles are big enough that you can see them, but they still stay dispersed throughout the medium or the liquid generally. And in suspensions, those particles are big enough and heavy enough that they can be filtered out, or they're so heavy that they fall to the bottom of the of your solution. So I'm going to give you a couple of examples here. One example of a colloid is milk. Milk has solid droplets of fat that are dispersed through the liquid portion of the milk. And if those separate out, that may or may not be a good thing. If they're separated out in their cream, that's a good thing. If they're separated out because your milk is sour, that is not a good thing. But generally speaking, the fat particles in milk stay suspended in the liquid medium of the milk. However, if we try to shine a light through it, the light's going to bounce off of those fat particles and reflect back. Suspension, this is the one you guys will all remember. If you remember being young, little, and having to take the pink bubble gum flavored antibiotic, you had to shake that up before you took it. The reason that you had to do that is the actual antibiotic, the medicine portion, was crushed up and suspended in that liquid pink matrix. And if you don't shake it up, then you don't get the right dosage of medicine, because the medicine pieces are so much larger that they don't stay suspended forever, right? So we're going to call this our pink antibiotic. Or you may remember shaking up Italian dressing. Oil and water don't mix, right? So if we're making a salad dressing of oil and water, we'd shake that up so that we get all of the flavor evenly dispersed, okay? So two general types of mixtures: homogeneous, which look all the same all the way through. You don't see the different parts that make it up. We also refer to those as solutions. Or we have heterogeneous mixtures that can be colloids or suspensions. And the difference between colloids and suspensions are if the pieces will stay suspended or if they're going to fall out. We don't get a lot of discussion about colloids, so I like to show you all this graphic so that you can see the different kinds of things. We tend to refer to these kinds of mixtures a lot of time as liquids, but as you can see from the chart, you can have two gases that mix together. So for example, and then what they're called, you can have a gas that is dissolved in another gas. For example, oxygen gas is dissolved in nitrogen gas, and that makes up air. Okay, you can have air or a gas that is dissolved in a solid, and here, according to the chart, you can see that it's called an aerosol, but that's a marshmallow. All right, you can have liquids that dissolve in each other. Two terms that you need to know about these mixtures, and that is miscible and immiscible. And actually, the cool thing is they do kind of what they sound like. If two substances, pick any off these charts, solid and solid, a liquid and a gas and a gas, if they will mix together uniformly, they're called miscible. So substances that will mix are called miscible, right? Mixable, miscible. If they don't mix together, so oil and water would be immiscible because they don't mix together. Or you can shake them up and they can mix together for a little bit, but if you let them sit, they're going to separate themselves back out. So the terms miscible and immiscible are important to remember when we're talking about our homogeneous and our heterogeneous mixtures, right? So let's go back to our tree. Matter, separated into two big categories. You're either a pure substance or a mixture, depending on if I can separate you chemically or if I have to do it physically. Then, if you're a pure substance, you're an element or a compound, depending on how many types of elements are involved in your formula. And in a mixture, you're either homogeneous or heterogeneous, depending on the size of the particles and how those particles behave.